Hi, I'm Nick. I'm a technical mentor for Team 2220. In a previous video, I talked about how to model a West Coast drive, but I thought I'd make a video now talking about the design of a West Coast drive. A lot of people consider CAD and modeling and designing to be the same thing. I think that there are two very separate skills. The mechanical action of pressing the buttons and making the shapes is very different from the actual act of designing something. So I wanted to spend a little bit of time to talk about all the things that I kind of took for granted in that video, about all the dimensions and why certain things were done that may or may not make sense, and I take a little bit of time to explain that, and also talk a little bit about the history of the West Coast drive. So a bit on that. So the West Coast drive was developed in kind of the early 2000s out west. Team 60 from Arizona and Team 254 from California really pioneered this drivetrain, and it's become extremely popular over on the West Coast, and that's why it's called that. The main thing that characterizes a West Coast drive, more than anything else, really, is this cantilever. Now, you'll find people around on the internet at events. Somebody who doesn't really know that much about it will talk a little bit about drivetrains, and they'll say, "Oh, the Kitbot, that's a West Coast drive." The Kitbot, at least now as of 2020, is not a West Coast drive. It's just a six-wheel drive. It's great. It's a great drivetrain. A West Coast drive is not, despite what some people tell you, it's not magically inherently better. You don't inherently win more because you have a West Coast drive. There are plenty of teams that win without them. West Coast drives just tend to be popular and have a bunch of features that make them really nice to work with. So I'm going to start by talking a little bit about something that I actually missed in that modeling video. It is really where I think a lot of the magic of the West Coast drive design comes in, and that's this setup right here. This Nautilus cam, which is called that for its shape, which is a nautilus, like the shell. This Nautilus cam and this sliding bearing block. So I'm going to use a feature from Onshape section view to take a look at what exactly is going on in there. And we'll cut it open just right to there. And you can see this setup basically. What you've got there is you have this sliding bearing block, which has two parts, right? It has this side, which is the part that's which is bolted to an exterior side, which has a countersunk screw, which I'm gonna hide that wheel. See, there's a little countersunk screw right here. That's a bad example because this isn't modeled super great. This countersunk screw that keeps that face nice and flat on the outside. On this side, we have some tapped holes, and here's where we put the Nautilus cam too, because otherwise it'd run into the wheel out here. And this is an evolution of years of design. There's been a whole bunch of different West Coast drive style designs, which again is defined by this cantilever. So a cantilever is when you have a shaft that's unsupported on the outside. So it's defined by these cantilevered wheels. In fact, doesn't matter whether there are 4 or 6 or 8 of the wheels. Doesn't matter whether there's belts on the inside or chain. Doesn't matter what motors are powering it. What matters is those cantilevered wheels. In this case, it's a setup called 4+2, so or 4x2. So you have 4 of these traction wheels and then 1 omni wheel in the back. That just helps you turn a little bit. So like we're talking about this sliding bearing block. And now this sliding bearing block is really nice because it buys you a lot of flexibility. You'll notice, right? Let's go back in. Turn a section view on again in here. You'll notice, right, that rectangle, which is what's sliding inside of this pocket, this very particularly shaped hole that we cut in the tube, has a little bit of play in here. In fact, it has about, let's redo that, sorry. So let's exit that real quick. All right. So you can look in here and you can say that has almost 3/8 inches of play. You notice, even though if you watch that previous video, I put this in the center, I put it back here in this. That doesn't strictly matter. If I wanted to change the mate connector to move it out, that'd be fine. But we get a bunch of flexibility here to tension this chain and to make up for those that extra whatever hundredths of an inch that make sure that chain is perfectly tensioned, which is what that Nautilus cam gives you. If you aren't familiar with the term cam, that just means that it's something that this will ride along, that'll push this out. So you can kind of think about it as I rotate this, it's going to push this block further towards the edge of the drivetrain, right? By tensioning the chain. So that's really nice. Really easy to change this. This is a what is that? That's a 3/8 inch. So you can just use a wrench to do that. It's great. Another thing I'll talk about in the way that this one in particular is designed, it's designed using exclusively these double sprockets. Use double sprockets for a few different reasons. One of the reasons is it means you have one part that you throw on all of them. It's only like $5 more, I think, on West Coast products for the double sprocket versus the single. Which does, that means you're spending an extra $30 for the drivetrain, but it also means that there's not a where did I put that specific sprocket, that I have one sprocket that's over here and a specific spacer for that, and one sprocket's over here and a specific spacer for that. This entire thing means that we have one size of shaft, we've got one size of spacer, we've got one size of sprocket. So assembly becomes a lot simpler on that, which is really nice. And it's not like you're really paying for a weight hit or anything. This also gives you a little bit of flexibility if you wanted to move things around, all sorts of stuff like that. I do 18 tooth on this. I did 18 tooth on this for the main reason of it. Just generally, you typically just want to use the largest sprocket that will fit, that'll do the job for you. And in this case, 18 teeth is the largest sprocket on there that still fits, including the chain, within this 2-inch tube. So I can still throw a belly pan on that if I wanted to. I could still do all sorts of stuff, and it wouldn't really matter. You'll notice this is slightly off. That's really not that big of a deal in this case. That just means that this spacer isn't the right length and this spacer isn't the right length. I'd go and fix that before I actually made this. So So I mentioned belly pans. A lot of people tell you if you're going to build a West Coast drive, you got to have a belly pan on the bottom. That's not strictly true. You can get away without a belly pan in many cases. That being said, oftentimes a belly pan is a really easy way to add some rigidity. So what happens in this case, where I have no sort of superstructure on top, I got nothing on top, I have no extra reinforcing frame members here, is that somebody comes and hits me really fast in this corner, and all of a sudden this nice rectangular chassis becomes a parallelogram. You get an angle on there, and that's not a desirable characteristic of a drivetrain. And you can fix that. You can make it more resistant to that by adding frame members front to back. You can get that by adding a belly pan that just goes all the way across and has kind of an X shape, at least here, where you're reinforcing it directly corner to corner. You've got material that's reinforcing everything. Belly pans are a great way to add electronics. Even if you don't have like a full belly pan, oftentimes it makes sense to throw at least some of your electronics in the base of the robot. Obviously, you can see we'd be running chains back here. So you want to be careful about making sure that they're not too close to this. When I go and I look through catathon robots, sometimes I'll see people throw electronics really, really close to these chains. Like they'll throw a power distribution panel right here. It's like, well, you got wires coming out this way. You got wires coming out towards the chain. You're going to want to be careful with that. So it's just something to keep an eye on when you're designing a drivetrain. One of the things that I did when I modeled this that is a little bit standard, non-standard. So it's pretty standard to make this entire thing out of 1/8 inch or 1/10 inch if you're using a VersaFrame from Vex Pro tube. In this case, I actually did an 1/8 inch tube here for the side rails, just because we have there's a lot going on with those. You don't want the side rail to break. You can get away with a 1/16 inch side rail. Personally, I just think it's silly to worry about that unless you really need to. So in this case, you got an 1/8 inch front rail. And you've got a 16th inch front rail, and you got an 1/8 inch side rail. And the 16th inch side rail, the 16th inch front rail, sorry, is, you don't need to worry as much about that. It's going to take some impacts from the front, but beams are very, the cross-sectional area of this, right, an impact, it's pretty tough to bend that, especially if you have any kind of frame members going in, going across this, or anything like that. So let's talk a little bit about the gearbox selection here. So in this case, I chose a standard gearbox from West Coast Products. It's a flipped gearbox. I kind of like the flipped gearboxes because they leave you a lot of space open in the middle to do what you want to do in the middle. Sometimes you want to throw electronics in there, sometimes you want to throw a battery there, sometimes you want to throw a mechanism all the way through the center. And in this case, you can get yourself you can get yourself a nice setup here. And this is probably about the smallest that you'd want to get it for this, but if you want to, you can throw another tube along here, another tube along here, and have just enough space in between them for the battery, which can be a nice little thing to do when you're designing that. West Coast Products also has some nice non-flipped gearboxes that can be a good option. They have some shifter gearboxes, all sorts of stuff. Like you can go wild with buying gearboxes. You can go wild with designing gearboxes. Personally, I kind of like to stick to either COTS or very simple gearboxes when it comes to drivetrains, just because it can be a hassle to get you the right tolerances. If you mess up the tolerances, you can get extra gear wear, and just overall you really just don't want to be worrying about your drivetrain. It's a silly reason to lose a match because your drivetrain broke. So I got a couple questions online about why I did the bumper mounts like this. So when you're talking about bumpers in FRC, there's some really key rules that are important to understand about bumpers. One of them is that you need to be supported a half inch from the corners. And another one is that you can't have too long of an unbroken span between support. Now, what support constitutes is fairly nebulous in FRC rule books. So in this case, we're just throwing really the lightest thing that we can across this. So a piece of tube that will act as a legal equivalent of support, even if it's not absurdly strong. And in this case, it probably is just plenty strong. So that's what that's there for. This is not the bumper mounting. You don't need to mount the bumper out here. The rules for how you need to mount the bumper are much looser than how you need to support the bumper. So we can mount the bumper using any number of methods that still use this. And potentially use this to you throw some C-channel around it or something to keep the bumper supported along that. Maybe you drill through that and throw some pins through there. There's all sorts of options for how to use this to support that. But before you get there, it's a lightweight way to do this. This is lighter. This is going to be lighter than extending this out, doing some more standoffs, and then running another full rectangular tube across here, which is nice. You can also lighten these pretty considerably. If you go back and watch, so Team 2468 Appreciate has been doing some really fantastic webinar videos, and one of the recent ones that they released was 1678 Stitcher circuits going through their 2020 robot design, and you can see that they used a pretty similar way to do this. I can't wait for them to release that CAD because I can't wait to dig into it. That's pretty much where I got this from, and I think they're a great team to emulate when it comes to how they do things. Final things. So final things, probably let's talk a little bit about wheels. So you got a whole bunch of options for how you do wheels on a West Coast drive. The way that you do a West Coast drive, where you have this cantilever, means that in this case, this is a bolt that you'd unscrew to remove the wheel. But you can also use like an E-clip or something like that. It means you have a whole bunch of options for what you throw on here. You can throw on these traction wheels from West Coast Products. You can throw on Coulson wheels from Vexpro. Vexpro has some really nice half-inch hex bore Coulson wheels. You can throw on 4-inch Omni wheels like we have here. You can split the difference. All great options. And this kind of brings me back to one of the other core things about design in West Coast drives, which is the concept of a drop center. I know that for some people watching this might be a review. For other people, it might be the first time you've heard of doing this. But what you can do is you can see on here that this block is higher than this block. These wheels, this center wheel is lower than these edge wheels. what that effectively does is it splits the drivetrain in half. It means that you're going to have most of the weight on 4 of these wheels at a time. And that if your effective support polygon from that is going to be the distance between these 2 wheels. So about whatever, 9-10 inches, right? By the distance between the centers of these 2 wheels. So you end up with about a, 10 by probably 20 inch support polygon here, which means that you can turn really easily. You're not going to get in a situation where you can't turn. There's a great white paper on Chief Delphi, might link it in the description, about the actual math that it takes to determine whether a robot can turn or not. The Cliff's Notes of it is just that if your support polygon is wide, you can probably turn. If your support polygon is long, you probably can't turn. So in this case, I have both that drop center and omnis in the back, which means that this is probably going to turn really easy. You're not going to have an issue turning with this in the same way that you might if I ran all traction, no drop center. Then I would have a really long one. I'd have like a 20 by, and actually that might work anyways, because that would be about a 20 by 20 wheelbase. So that's basically a square, which may or may not work. Have to plug in the numbers. You're running the edge on that one. Anyways, that's pretty much it for talking about West Coast Drive design concepts. I'd love to hear any opinions on stuff you think I missed. Talking about how to design one of these. I've designed a lot of West Coast drives. I have not designed nearly as many as some people, and I haven't run nearly as many in competition as some people. So I'm sure there are a lot of great perspectives out there in the community. Thanks for watching. Hope you watch something else. Get some more stuff out there soon.